Now we are going to talk about polynomial functions and models. Polynomial functions and models. Well, we did talk about polynomial before. Now, this chapter, this topic, we're going to talk about, polynomial function, and we're going to talk more about polynomial function and basically general behavior of polynomial function. So what's polynomial function? Well, let's check out definition. Definition of polynomial function. Polynomial function is function of the following form. Say fx equal a n x to the n plus a n minus 1 x n minus 1 plus dot 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 a1 x 1, but we don't really write 1, but let's just write 1 for now, and a0 x to the 0, but x to the 0 become anything to the 0 power becomes 1, so we just have a0, where an minus 1 dot 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 a1 a0, these are all real number, and n, I'm talking about these n's, I'm talking about this n, this all n is non-negative integer. So what do they mean by non-negative integer? Well, they are saying it's not negative, and it can also be equal to 0 if they want to, right? So this is basically the basic format of what we call polynomial function. So now the degree of polynomial is the largest exponent of certain polynomial. Let's say, example, let's say we have fx equal 5x to the 7 plus 6x to the 4th minus 3x squared plus 4x plus 10. Let's say we have something like this. Now you notice that we don't have to have every single x term, right? We don't have x to the 6 or 5. We don't have x to the third. That's okay, right? You don't have to have all the term. Meaning, for that particular term, the a is going to be 0, right? We can think of it that way. What I'm just saying is this. I mean, for example, 0 times x to the 5. What is that? That just becomes 0, right? So we have x to the n certain x terms, but since these a's can be any real number, it can be 0, so it can go to 0, whole thing go to 0, right? So it's quite okay to have a couple of missing terms, right? So what's degree of this polynomial? Degree of this polynomial is going to be 7. Highest exponent, highest power of this polynomial. So this polynomial, this particular polynomial is degree 7 polynomial, right? no big deal. All right, so we talked about this before. Why do they making such a big deal out of whether it's being polynomial or non-polynomial? Because if it's polynomial, let's say we have these two different settings. We have these two different settings. This is polynomial. Let's say this is non-polynomial. Then polynomial graph is smooth, continuous graph like that. Non-polynomial graph will have certain change like that and some discontinuous, right? It's changed suddenly like that and it's discontinuous in here and here. So polynomial means it's going to be smooth continuous curve. All right. So polynomial, people like to work with polynomial for some obvious reason. Why would you want to work with a function that's not continuous and you can't really explain what's happening here and there's a sudden change and you don't really want that, right? So if they have a choice, they would love to work with polynomial equation and polynomial function in the same way, right? Okay. Now let's talk about power function. Power function. Okay, power function. Power function is basically a function, a single term function, and it looks like this. Fx equal a x to the n. This should be power function. Power function of n degree. N degree. Why is it n degree? Because that's n, right? So, example, if we have fx equal, say, 3x to the 5, this is power function of 5 degree, right? So no big deal. It's just power function, just have a single term, and that exponent is going to be degree of that power function. Okay. Now let's talk about multiplicities. Right. More up. Multiplicity. So we give you the definition first. If x minus r to the m is a factor of polynomial, function f, and x minus r m plus 1 is not a vector of f. Then R is called a zero of multiplicity M of f. You know, that's an interesting definition, and that's quite handful, right? So we are going to try to understand what they are trying to say. So basically what we're trying to do, we're trying to actually define a zero of multiplicity M, right? That's what we're trying to define. And they say this x minus r to the m is a factor, right? Is a factor of a polynomial f. And they say this is factor, but this should not be the factor. M plus 1 should not be the factor. Well, let me give you an example. Let's say we have fx equal x minus 2 to the third. Now, what's the factor of this polynomial function? What's the factor? Factor. Well, factor, you know, can be factor can be x minus 2 to the 1. Factor also can be x minus 2 to the square. Factor also can be x minus 2 to the third. Can't really see 3 to the third. Why is that? What's factor? Factor is the one that you can divide the original form, then you will get no remainder. That's another definition of factor, right? So, you know, for example, if you have like 8, what's the factor of 8? It's 1 and 2 and 4 and 8, right? If you divide 8 by 1, what's the remainder? Nothing. If you divide 8 by 2, what's the remainder? Nothing. If you divide 8 by 4, what's the remainder? Nothing, and so forth. So when you have this original function, if you divide this by x minus 2, of course you will have no remainder. And that goes same for x to the square, x to the third. So that's what they're saying. If one of these are factor, m plus 1, which is in our case would be what? X minus 2 to the 4. Is this a factor of this? No, this is not a factor of this. So when they say this is, when we have a situation like this, then that m must be same as this number, which is the highest power of that particular part, right? So x minus r to the m is a factor of polynomial, this polynomial, and not one bigger than this, right? In our case, 4 is not a factor of this. Then, because like I said, you know, if we have this and this also can be a factor, right? But m cannot be these two, because m plus 1, which is 3, is also a factor. But 3, if we say m is 3, then m plus 1, 4 is not here, so it's not a factor. So m must be 3. Now that m, this m, which is equal to 3, what do we call this? We call this as a zero of multiplicity 3 of this function, multiplicity of 3 of this function. Okay, so if we have, let me give you another example. Let's say we have f of x equal 5 x minus 2 x plus 3 to the square x minus 1/2 to the fourth. Okay. You know what? Multiplicity of 3, but I forgot to explain this r thing. So this r, in our case, this is r right here, right? This is r right here. So we should say 2 is a 0 of multiplicity 3 of f. That's quite handful, but we should say this r, which is this 2, right? This 2, because its setting also was x minus r. So if this is minus 2, then this is going to be our r. So 2 is called a 0 of multiplicity 3 of this function. So, you know, this example right here, let's check this one here. R should be 2. So this R2 is what? 2 is 0 of multiplicity 1 of f. Why is it 1? Because, you know, if there's nothing, then means there's a hidden one there. What about from here? R should be, remember the setup was Rx minus R. What if we have plus 3? Well, then it's going to be negative 3, right? The opposite. If this was a negative 2, then we just say 2. If there was a plus 3, then we say negative 3. So 3 is 0 of multiplicity of what? 2, right? So 2 of f. Now we have one more right here, right? So r equal, in this case, is 1/2. So 1/2, oops, not 1/3, 1/2 is 0 of multiplicity 4 of this function f, right? This function f. So we talked about the multiplicities and we talked about the zeros based on this definition. Okay. Now, so let me give you the setting. So we had x minus r to the m setting, right? So if R is 0 of even multiplicity, then what happened to the graph? The graph of f touch the x-axis at R, right? And if R is 0 of odd multiplicity, then the graph of f cross the x-axis at R. Whatever that means. Whatever that means. Well, they're talking about this. You know, this previous example right here, we had 2 as a 0, 3 as a 0, and we also have 1/2, -3. Oh, I forgot negative. Sorry about this. You know, this should be this, -3. So 1/2 is also a 0. But this 2 is 0 of multiplicity of 1, which is what? Which is odd. If it's odd, then the graph is going to cross at x equal 2. And this -3 is zeros of multiplicity of 2, which is even number. That means what? The graph of this function, we don't know exactly what it looks like, but it is going to touch at x equal -3. What about here? This is multiplicity of 4. So again, even number, then it touch. Right? Even number, even multiplicity, it touch. Odd multiplicity, it cross. So let's revisit this example that we had previously. Say f of x is 5, x minus 2, x plus 3 to the square, and x minus 1/2 to the 4th. So we have zeros as 2, -3, and 1/2. What was the multiplicity of this? 1. What about this? 2. What about this? 4. Meaning what? This will cross, this will cross, touch, touch. So we do not know exactly what this looks like, but let's say we have -3. Let's say we have 1/2, and let's say we have 2. The graph is going to cross at that point, right? Cross. So it's going to cross here, and it's going to bounce it back to touch here. Touch here and touch here, right? So it's going to touch here, not going to go cross. It's going to bounce it back to touch. And it's going to touch here again. It's going to go up, and it's going to bounce it back. It's not crossing at that point. It's going to touch at that point. So by analyzing this multiplicity and the zeros of this function, we have a fairly accurate general idea of what this function should look like, right? What this function should look like. All right.